The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and welcome to our webinar, Broadening Horizons, 5 Fields Where Viscosity is Key. In this webinar, we're going to be exploring 5 common application areas where viscosity is a key parameter. The webinar will be hosted today by our in-house rheology experts, Dr. Stacey Elliott and Dr. Zachary Imam. Dr. Elliott obtained her extensive experience in rheological knowledge through her education at Carnegie Mellon University in Princeton, as well as her experience at both Alcon and DuPont. Dr. Imam obtained his PhD in biomedical engineering from the University of Texas at Austin and spent a year postdoctoral continuing development on a bioscience project funded by the Department of Energy's Basic Energy Science program, studying the biophysical properties and functions of microtubules. Without further ado, it is my pleasure to turn it over to Dr. Stacey Elliott.
Hi, everyone. Welcome to the webinar. This is Stacey. There we go. So as Eden just said, we're going to broaden our perspective today. Typically, since much of our customer base is in the pharmaceutical industry, we talk a lot about antibodies and proteins and applications of that sort. So today we wanted to talk about some other areas where viscosity is a very important parameter. And in fact, there are a number of fields, even beyond the 5 that we're going to discuss, where viscosity is a very well-established characterization technique. And some clear correlations are made between performance and the rheological properties of the materials. So we'll move on then to what topics we intend to discuss. But that's the gist behind this. We want to emphasize that viscosity plays a very important role in a variety of industries and is well established in certain and is emerging in others. Okay, so just a quick overview of what we'll go over today. So just, I know a lot of you are returning to our webinars and have heard us discuss viscosity and what viscosity is before, and also discussing our VROC technology. But for anyone who's new to the topic, we'll just do a quick 1-slide review of both of those, and then we'll go into the content. So the 5 areas that we were going to talk about, we're going to start with industrial polymers, specifically polymers in the role of rheology modifier and what that means. And then this kind of feeds into 2 of the topics, that being the food, beverage industry and personal care products. Rheology modifiers are commonly added in both of these types of formulations, so we'll touch on that a bit. And then we'll move into cell culture media. So this is distinguished from the other industries or applications because these are very low viscosity Newtonian fluids. So this is kind of emphasizing somewhat new application area, but then also emphasizing the ability to differentiate small viscosity increments of these low viscosity fluids. And then finally, another newer area of where rheology or viscosity specifically is emerging, and that is in the cannabis industry. And these again are highlighting some other capability of our instrumentation, mainly that these are extremely, for the most part, high viscosity oils and quite temperature sensitive, which is sort of the relevant test that we would perform. So let's first start with our quick review. So just for anyone new to our technology or Rheosense, our technology is referred to as VROC, viscometer rheometer on a chip. And what our technology does is it measures steady shear viscosity using a combination of microfluidics and MEMS. So we have a well-defined microfluidic channel with pressure sensors lining the base of the channel so that we are controlling the flow rate into the channel using the pressure drop across the channel to calculate shear stress. So the steady shear viscosity, as many of you know, is defined as the proportionality between shear stress and shear rate or rate of deformation. So it's a calculated property where shear stress, as stated, is coming from this pressure drop across the flow channel, and the shear rate is defined as the gradient perpendicular to the direction of flow, the gradient of the velocity perpendicular to the direction of flow. So this is the sort of schematic of what the flow field looks like in our flow channel, and details on how we calculate everything. Because remember, viscosity is always calculated. So with that in mind, so all of the data that we will present today was collected in-house on our own materials, so nothing proprietary, and all collected using our technology. So starting off then, we wanted to talk about industrial polymers, particularly their role as a rheology modifier. So other terms that you might have heard to replace rheology modifier or to be synonyms of are thickeners or viscosity modifiers. That kind of presents a narrow view of the topic, because that kind of makes you think, well, we're just going to try to shift the overall viscosity up or down in some manner. But there's actually a lot more that goes into the field of rheology modifiers, because the idea is that you can use them not just to shift things up or down, but actually to control the entire viscosity profile. So what we have here is some example data and a model fit to extend it beyond what we can actually collect. This is viscosity as a function of shear rate. And so if we're careful in choosing our particular polymer that we're using as a rheology modifier, we can really control the nature of this entire flow profile. By that, I mean the magnitude of both the low shear Newtonian plateau and the high shear Newtonian plateau. Also the onset, the critical onset, where does shear thinning occur? And then what is the range of this thinning that exists? Over how many decades of shear rate does it take to go from to bridge between the two plateaus? And then another consideration when choosing your viscosity or rheology modifier is thixotropy. So in this instance, that's the time dependence. So if we shear it down, how quickly do we recover back the structure that these rheology modifiers are basically creating in our fluid? So that it's really, the term sounds quite simple, but then you're really able, if you're experienced in choosing the appropriate molecules, able to do very precise control over your entire viscosity profile. And you can essentially also trigger certain behaviors as you change the environment. So a lot of these polymers are sensitive to different aspects of the environment. So water-based or aqueous polymers can be sensitive to pH and ionic strength. So ionic strength, both the level of salt and the type of salt, can be very important to the behavior. And if you're dealing with organic systems, then in that instance, you can adjust behavior by adjusting the solvent quality, by adjusting the solvent, using solvents with different solvent quality. So poor to, say, good solvents. And then also, and we'll talk a little bit about an example of a thermo-responsive polymer, you can have some very interesting behavior depending on the temperature. And the idea is that you're adding this polymer in that can, in certain instances, be the active ingredient as well. And we'll talk about a couple examples of when that is the case. So your rheology modifier can also be one of the active ingredients, or it can just be added intentionally just to control the rheology and not really necessary for the other properties of your formulation or system. Okay, so starting off then, as I said, what we wanted to talk about some rheology modifiers that would sort of feed into the food, beverage industry and some personal care products. So on the left, we have a common rheology modifier, and actually this is the case where you would have a polymer that is both controlling the rheology and also an active ingredient, particularly in skincare or cosmetics. So the sodium hyaluronate or hyaluronic acid, in addition to being a high molecular weight polymer, is also quite hygroscopic. So it retains and attracts moisture. So this is why it's a very attractive polymer for skincare, and then also it's used in eye drop formulations as well. And you can see on its own, so this is just hyaluronic acid or sodium hyaluronate in deionized water at 1%. The viscosity is a function of shear rate. This on its own is quite shear thinning. And although we didn't quite illustrate it here, in addition to varying temperature to vary the rheological behavior. So here we're spanning between sort of relevant temperatures for either say eye care products or personal care products from say cold room temperature to skin or eye temperature. We've illustrated that here, but you can also then clearly adjust the behavior by changing your weight percent or content in the formulation. Another example that's going to pop up in some of our other applications, I think it shows up in both actually food and the personal care. And then also some of our, we know from working with some of our paints and coatings customers that they actually use these in that industry as well. So these sort of span a variety of industries even beyond what we present here. So in this case, again, our particular samples, we don't know the exact molecular weight of this one as we did with our sodium hyaluronate, but this tends to be even high molecular weight, 1 million plus generally. And again, you can see as we adjust the concentration, and these are quite low concentrations because these are quite high molecular weight, and it is each individual monomeric unit is quite bulky, lending a lot of interesting rheological behavior. But we can see that we can adjust plateau values, range of shear thinning, and both low shear plateau and high shear plateau by adjusting the concentration. And although we didn't, we're limited in time, so we didn't go into it in too much detail, but you can start also varying the behavior of these by adjusting the nature. These are all aqueous based, so you can vary, as I said, the ionic strength and pH, and then further tune these as well. So one final rheology modifier before we get into some of the applications. This is one of the thermoresponsive types that I mentioned or hinted to early on. And by thermoresponsive, what happens is now instead of a homopolymer, which we just discussed in terms of the sodium hyaluronate and the xanthan gum, this is a diblock copolymer. So now we have different blocks that have different behavior. And specifically, this mid block, because of this methyl group, is more hydrophobic. So when we put this in water or some buffer type formulation, and again, this will be sensitive to things such as pH and ionic strength. Now we have the ability for this to self-assemble because we have blocks that are more hydrophilic, blocks that are more hydrophobic. And this, the nature of the hydrophobicity and therefore the nature of the self-assembly is highly sensitive to temperature. Because one of the things that changes in these aqueous systems with temperature is the extent of hydrogen bonding because of the thermal motion and whether it's faster or slower depending on temperature. So a common application for these types of materials, and these are referred to the trade name, one of the trade names, there are multiple ones, are polymers. So one of the applications of these then is if you want something that is lower viscosity at, say, room temperature, but then when it is introduced into the body or onto the skin, the viscosity either increases or the material even gels. So for these types of, sorry about that, for these types of materials, there's actually a phase diagram. So if we look at the temperature as a function of concentration, you can actually develop this for your particular poloxamer, which can vary in terms of overall molecular weight and the ratio of the blocks. So what you can do then is find out, for a given concentration, what temperatures are you in a viscoelastic solid gel type state and what temperatures are you in a fluid state. And the viscosity measurement can sort of guide you in developing this phase diagram. And so what we have here are one of the particular poloxamers, the P407, which is the one that kind of peaks in viscosity close to body temperature or skin temperature. And we can see, in addition to the temperature sensitivity of the relative viscosity, we can also see the sensitivity of the concentration of this particular poloxamer. And So this is just a more complicated type of rheology modifier if you want to introduce temperature sensitivity and see a transition from potentially something that is a low to moderate viscosity fluid to something that is a viscoelastic solid or a gel. So the first application where we can sort of see how these rheology modifiers might play a role in the viscosity of some particular products is the food and beverage industry. And our two examples here are contrasting sort of simple fluids with small molecules only versus some formulations that have introduced these high molecular weight polymers as a rheology modifier. So we'll do the simpler products first. So on the right-hand side, we have a variety of alcoholic beverages, so a variety of wines and some liqueurs, whiskey and such. So we can see the viscosity as a function of shear rate, and all of these over the range that we've tested and likely over any accessible range are going to be Newtonian or shear rate independent. And you can rationalize this based on your knowledge of what is actually in these fluids. These are all small, simple molecules that would not produce any non-Newtonian behavior, particularly shear thinning is what we're mainly talking about here. Because what we have in here are alcohols or alcohol, water, sugars, and a variety of small molecule flavorings. So no surprise then that these are shear rate independent or Newtonian. However, if we look at some food products, and so these are syrups, and what we were comparing are the real deal, real maple syrup, versus an imitation syrup that you would buy, so pancake syrup or whatever name they go by, and then a mixture of the two. The main purpose of this actual testing that we did was to see if we could, there was some suspicion that people were trying to sell something, labeling it as real maple syrup, but to save money, they would cut it with the imitation. So we were seeing if we could rheologically, go in there and investigate and see if something was not the real thing, but rather, cut with some of the imitation fake syrup. And so what we can see is that the real maple syrup is Newtonian over the range that we tested. And as we'll when we discuss what's in maple syrup, it would likely be Newtonian over the entire range that you could get if you were combining multiple types of instruments. But then the imitation syrup is extremely shear thinning over this range of shear rates. And the mixture also has some degree of shear thinning, although not quite as much as the full strength imitation syrup. So if we look at the real maple syrup, which has Newtonian behavior, again, this is primarily composed of very simple molecules. So most of the sugar is in the form of sucrose, and then of course there's water in here, and then trace minerals and vitamins. Nothing. All the other molecules would be then small molecules, nothing that would contribute to any non-Newtonian behavior. However, if you look at the imitation syrup, which does have this non-Newtonian or shear thinning behavior, and you look at the ingredient list, the final ingredient on the list is xanthan gum. And so what we just saw when we were talking about the rheology modifiers, that this is a very high molecular weight, bulky polymer, that even in very low concentrations is going to introduce a significant amount of shear thinning behavior and increase the viscosity. So even though it's in there, based on it being last on the ingredient list, it's in there in a small quantity, we can see that it has a huge impact on the rheological behavior of this syrup. So this is an example there of these rheology modifiers and what they can do versus very simple fluids with small molecule behavior. So now I'm going to pass things over to Zach, and he's going to talk about another industry where the rheology modifiers are commonly used.
Thanks, Stacy. Picking back off of what Stacy was just talking about, rheological modifiers are very important in different fields. And so here I focus primarily on personal care products, specifically on the left, colognes, and on the right, eye drops with two different types of polymeric ingredients. So let's begin with the different colognes. So colognes are primarily modified with just changing the ratio of alcohol and whatever the molecule, the small molecules that give off the pleasant smell. And so as you can see, these are Newtonian fluids primarily, and that makes sense because all of the molecules within the formulation for a cologne are small in scale and don't undergo major changes when induced under shear, induced to flow under shear. And so these differences between this cohort up here and this cohort down here is primarily driven by the alcohol content. And I believe this cohort primarily has about 83% alcohol by volume, and this cohort down here is closer to 80% or 81%. And then over here, we can look at the differences between the polymer that Stacy described earlier, sodium hyaluronate, and hydroxypropyl guar, which are two commonly used polymers in eye drop formulations. And we can see that at low shear rate, they're very distinct. But then as shear rate is increased under high shear, they then collapse upon each other and behave more similarly. And so this kind of demonstrates why it's important to have a broad shear rate range when undergoing rheological tests, because you can fully understand the behavior of your polymer or your formulation, excuse me, based on the polymers within that formulation, how it's going to behave under different environments. So at low shear, that's what it behaves like under storage conditions, or when you're first acquiring the sample from whatever container you have it in. And then the high shear environment is likely what it experiences under use. So as we can see here, sodium hyaluronate has a lower viscosity than hydroxypropyl guar at this low shear rate range, but at the high shear rate under application for environment, they begin to behave similarly. So the customer will not really be able to tell a difference. So this can kind of help guide, say, your quality control, for instance. And then moving on to other products. So on the left, I have serums, so like skin serums. And on the right, I have lotions, like face lotion, aftershave lotion, face lotion, and just general lotion. And again, it's all about the rheological modifiers that you put into your formulation. So on the left here, we have 3 different serums, and they have 3 different types of behavior. The black sample we purchased, it's, I believe, called Josie Moran. In this sample, it is Newtonian across the entire shear rate range that we tested, and that made sense based on its formulation, which was primarily composed of different oils. And then these other 2 serums we purchased, this Revitalift and Prism serums, we looked at their ingredients list and found that they had both xanthan gum and hydroxypropyl guar, and thus we were able to see shear thinning behavior across the same shear rate range that we tested this Josie Moran formulation. And this kind of pinpoints how dramatically different formulations can behave, and it's based primarily on the rheological modifiers that you put in your sample. And so over here on this chart, we have 3 different face lotions, shave lotion, Olay face lotion, and 3-in-1 generic lotion. We can see they have very consistent behavior. They're all shear thinning, and that makes sense given the xanthan gum, the stearyl alcohol, the PDMS, and all sorts of the other rheological modifiers that are in the system. And so all of these formulations behave similarly, but they all have different viscosities and different behavior. And so the shave lotion is generally higher in viscosity than the face lotion and the 3-in-1 generic lotion. So kind of like an in-between the two with different applications in mind. And so when you're producing your products, you want to kind of have a goal in mind. What is the application that I want this product to perform under, and what types of properties do I need it to do when it's being applied? And then you can use rheology to test and see how it does behave under these conditions, and see if it meets whatever criteria that you set when you're early on in development. And then you can adjust your formulations accordingly if it's too high in one region and too low in another. And so another application that viscosity can be extremely important is actually in cell culture media, which is very important to the biotechnology industry. If you're developing drugs or developing diagnostic tools that work on human cells, then you inevitably will need to have cell culture media somewhere in your development pipeline, or at least using it somewhere in your development pipeline. And it's required for cell growth, just feeding the cells and having them grow. It's important for cell proliferation. So when they're dividing, they need certain chemicals at certain times in order to divide properly. And then if you're working with stem cells, you need different cytokines and chemokines delivered at specific time points during the cell growth process in order for them to differentiate properly. And all these different modifiers can also change their rheology and can lead to interesting phenomena, especially with certain stem cells and differentiation. There's certain types of cells that can only differentiate when they're exposed to a shear stress of some kind. So rheology is very important in those cases. And so whether you're in the basics, studying basic scientific questions, trying to understand the fundamental cellular processes in the cell, or just trying to study how stem cells behave under certain stimuli, whether you're developing drugs, trying to develop regenerative medicine, growing organs, growing lab-grown meat industry, organ-on-a-chip industry, all these different fields all require cell tissue culture, and it's a very important part of the process. And so some things with cell culture is the formulations are all very, very similar, using very similar ingredients. And so how do we differentiate between two? So we have two large groups of media. We have natural media like fetal bovine serum or horse serum. And then we have synthetic media like Eagle's minimal essential media, Gilbecco's modified Eagle media, which is more common, HAMS or F12 media, which are also used in, the first three are all used primarily with mammalian cells, and then there's Grace's media, which is used primarily with insect cells. So each of these different medias all have different ratios of nutrients and all behave very similarly to the naked eye, but they all have subtle differences that may be important when working with cells. And so primarily the main media components are a sugar, typically dextrose, amino acids, salts, and vitamins. And these all range from low to high concentration. So with the sugar, it's 5 to 25 millimolar. Amino acids, the highest concentrations are 1 millimolar. Salts can range from 100 to 150 millimolar of like sodium chloride to 10 to 50 millimolar sodium bicarbonate. And these salts can dramatically influence the viscosity if it's too high or too low. And then the vitamins are very, very dilute. And so one question we were trying to answer here was, can we differentiate between these very, very subtle, subtly different fluids? And so we began with Gilbecco's modified Eagle media, or DMIM. So on the left here, we have the low glucose formulation, which is 5 millimolar, and the high glucose formulation, which is 25 millimolar. And we were able to tell a difference between the two. It was small, but statistically significant. We purchased these media from, I believe it was Thermo Fisher, and they have a proprietary nutrient blend called Glutamax, which has some glutamate in it, among other things. And so we wanted to test and see if there was a statistically significant difference that we could detect between two formulations, and we could. It is small, but statistically significant. So then we moved on to AMS media or F12 media, and we were looking to see if there's a difference between filtering the media or unfiltering the media, and then there's also a 50-50 formulation of F12 and DMEM, and we wanted to see if there was a difference between purchased and homemade. So we took our high glucose DMEM and our F12 media, mixed them together at a 50-50 ratio, and then compared that to the purchased formulation. And we determined there was no difference between those groups, but there is a difference between the F12 and the DMEM. I believe the F12 has about 10 millimolar glucose, while the high glucose DMEM, like I said, has 25 millimolar glucose. So we then looked at fetal bovine serum, which is a supplement typically put in cell culture media and mammalian cells to help them grow and proliferate. And we again looked and see, does filtering have an impact on the viscosity of the FBS? So filtering is very, very important when working with cell culture media. You do not want bacteria or foreign cells growing out of control in your cell culture dishes. That will ruin all of your experiments. It's especially damaging to stem cell research. You can lose lots of time, be set back months if you have a contamination. So it's imperative that you have sterile materials when you're working with cells. And so we wanted to look at filtered versus unfiltered, and there was no difference. And then we wanted to see how does the combination of FBS and different mammalian medias, how does FBS influence their viscosity, since FBS is a little bit higher viscosity than the standard DMEM or F12 media. And as expected, as you increase the concentration of fetal bovine serum in the formulation, the viscosity increased accordingly. And we varied the concentration from 2.5% all the way up to 25% FBS, which covers basically the entire range of experiments and formulations that I've seen in the literature for supplementing your media with FBS. And so I was thinking, well, maybe we can be able to predict the viscosity of our media, our supplemental media with FBS. So I just did a simple expected value calculation, the percentage of media times the viscosity of only media plus percentage of FBS in the formulation times the viscosity of FBS alone. And interestingly, the low glucose DMEM and the F12, which is also low glucose in comparison to the high glucose DMEM, both were able to predict the viscosity quite well. However, the high glucose DMEM, it was very difficult to predict the viscosity. Although it's a subtle difference, it's still a difference. And I attribute that to some form of interaction between the glucose and the nutrients in the FBS. So I guess my conclusions are, what was the primary driver between these subtle differences between the F12 and DMEM media formulations that we were able to detect in the VROC? I concluded that dextrose or glucose is the likely primary contributor to these differences. It's a large molecule in comparison to amino acids, salts, and vitamins. And also between the formulations I looked at, the concentrations of amino acids, salts, and vitamins were too similar to really attribute these differences to those specific nutrients. However, the differences in viscosity really strongly correlated with the increasing glucose concentration between low glucose DMEM and F12 and the mixture and the high glucose DMEM. And then also at some level, FBS and glucose interact is the basic conclusion that I got from these experiments that I ran. And so that concludes my part of the presentation. Stacy will now finish it off with Cannabis Rheology.
Okay, so the final section we wanted to talk about for a couple reasons. One is that it's sort of a newer area for us that we've seen grow over the past couple years. We've had more and more clients in this area. And then also it kind of highlights the range, the range of our instruments. So whereas Zach just talked about distinguishing these very low viscosity fluids, cannabis oils are kind of the opposite extreme of that, where these can be very high viscosity. And I'll emphasize that some more when we get to the data section. But so when we deal with the customers working with the cannabis oils, a lot of the customers are dealing with the vape pen or the vaporizing pen. And so what tends to be important is the temperature variation of the viscosity as applied to these oils. And just a very basic view of the vape pen, I want to focus in on the cartridge region, which is, where the oil is stored, and then the atomizer where there's a heating element, which is where the vaporization is intended to occur. So thinking about this region in particular, viscosity is, as it turns out, a very important property in proper functioning of this product. Because if the viscosity is too low, then we can have flooding, essentially, of the heating element. Viscosity is too high, then you can have clogs in the cartridge, or you can have, rather than vaporization, you can have combustion or burning of the product on the heating element, which you would not want. So also, because these cannabis oils that come in the cartridges have a variety of formulations, just everything from ratio of components to flavorings. You can have a very broad range of viscosity depending on the exact purpose of the product. And as I said, the temperature dependence is important to these particular customers, mainly because of the presence of the heating element in the atomizer. And then also they've talked to us about extreme use or storage conditions. So they're concerned with things that can happen if someone is using this in, say, Minnesota versus Texas. So with that in mind, I just wanted to show some data so you can clearly see how different these are than some of our other products. So in this particular slide, we're going to focus on temperature dependence. So both plots are viscosity versus temperature. These are just generically labeled as they were provided by a customer. They've authorized us to use them, but without acknowledging what they are. So so what you can see is we've measured these. These are doable on both our MVROC system and our Initium. MVROC is probably the better option because we can get to lower temperatures where we see very high viscosities. So in this case, where for one of these oils, we're approaching almost 100,000 inverse seconds at something close to room temperature. And I think just the highest one we've ever measured, although I don't have that data presented here, was about 300,000 inverse seconds. Or I'm sorry, 300,000 centipoise. So these can get very high viscosity, and as I stated, there is a significant temperature dependence. Although we don't have true model fits to these, they tend to follow either an Arrhenius or modified Arrhenius law, which can allow you to do some extrapolation. But you can see the temperature sensitivity, and you can see how high in viscosity these can get as we approach room temperature. And then you can imagine if you get to colder temperatures, as I said, they're concerned about extreme usage environments. So if you get to much colder temperatures, these would be extremely high viscosity. The last point I wanted to make about these is just to emphasize the composition dependence. So these were just some commercial products that we purchased here, and we can see some of the ingredients in these products where they look seemingly modest changes in composition, whether it's the THC or the CBD content of these. And the composition seems to vary depending on the specific intended use. But you can see that even these modest changes in composition we can see nearly an order of magnitude difference in the viscosity. Again, viscosity is a function of temperature. And in this instance, we did use the model fit to sort of extrapolate back down to cooler temperatures, since this also was measured in our automated system, and getting down at these low rates, low temperatures, extremely high viscosities wasn't really possible. So they're quite dependent on composition. Seemingly similar products will have quite different behavior. So with that, we'll stop and take any questions that you might have, but I'll just quickly summarize. We tend to commonly focus on proteins and antibodies as it's a big topic of interest for our clients, but we did want to emphasize that rheology, viscosity in particular, is used across many industries and is actually a well-established characterization technique in many of those, such as personal care, food, paints, coatings, which we didn't address. But then it's also emerging in some of the newer industries, such as the cell culture media and the cannabis oils. So there's a lot of opportunity for growth there as well. And also, if you look at the established industries, I think there's a lot you can learn from those and adopt as we move it into new areas. So we'll take a look at questions now. Okay, so we have a question about, so a lot of our data here is showing shear rates at 100,000 inverse seconds or greater. And then the question is, where do shear rates of this magnitude occur? One of the common ones, and of course this wasn't the topic for today, but I'll use it as an example and then kind of move on from there. So if you're dealing with, we talk a lot about injection force because this, as I said, we deal a lot with pharmaceutical products. And in that instance, the flow through the needle is quite high shear rate. And the reason it's a very high shear rate is because the inner diameter is very small. So in any situation where you have flow through a very narrow channel, then you have the potential for these extremely high shear rates. Also, you can have very high shear rates in other circumstances where you have small length scales and fairly rapid movement of a surface. So for example, shear rates estimated in the blink cycle can also be quite high in that range. So, and I expect that, certain processing conditions, mixing perhaps, or, if there's transport in a narrow channel, then that could be relevant as well. And perhaps also, spreading of, say, topical skincare products there, because, there's variability in the rate at which you are applying them, and the film thickness is very thin. So those are sort of the two factors if you're thinking about how high will your shear rate be. What is that characteristic length scale, say a thickness of a film on your skin, and how rapidly are you moving the counter surface across the skin. So I would say applying something to the skin, maybe even in paint application where you have, again, thin films and potential rapid movement, blinking in the eye, and then, of course, a flow through, say, a needle. Can you think of anything else, Zach?
Only other thing would be like vortexing or high-speed mixing.
Yeah, and yeah, so a high-speed mixing, there your length scales are large, but your motion is very rapid. So look for rapid motion or very small length scales across which your velocity gradient would occur. Okay, the next question. Okay, in the viscosity versus temperature plot, why were there two curves per concentration? One for heating and one for cooling, or is there a different reason?
Polymers data.
So if you're referring to the Polymers data, so this is the thermoresponsive polymer. we had two curves. One, yes, was for heating and one was for cooling. And so the purpose of that was to illustrate that this is a reversible process. So certain changes in rheology that you see with temperature can be irreversible, such as denaturation of proteins. But in this case, where we have self-assembly, that self-assembly of the peroximer molecules is reversible. So we were doing that to illustrate the reversibility of this change in structure and therefore change in viscosity. Okay. So the next question is if we have any tips when you're working with a variety of samples applications on cautiously approaching measuring the viscosity. Okay, so that's a very broad question. With this, we have a follow-up here, so maybe that will help us narrow down the answer. Okay, so a follow-up to that question. So looking for tips on when you're measuring viscosity, I guess maybe when you're dealing with a new sample, and what's a common mistake people have when approaching measuring the viscosity. So I would say, if you're dealing with a new sample, or even maybe if you're just new to the technique in general, is that you want to sort of go in with an open mind. And by that, I mean, it's fine to use, particularly if you're in the research and development area, it's fine to use established protocols, but I would use those as a starting point and then let the data kind of guide you as to where you want to go next. So starting off, I would recommend trying to get as broad range of data as you can that would be relevant to you. So by that I mean shear rates, and getting a broad range in shear rates is important both for finding rates that are relevant to your application, but then also just to develop a basic understanding of the material. So to see, it can be quite informative to see, even if you're moving into rates that aren't particularly relevant to your application, to see how it behaves across that range, because then you can interpret something about the microstructure and the interactions that might be occurring there. So I would try, at least when you're starting out, to go as broad as possible in shear rate. And then also if, temperature is a relevant parameter for you, maybe for your application purposes, try to explore that as well. And just to get an overall broad view of what is happening. And then, depending on what your goal is, then you can maybe in the future narrow things down and simplify your testing. But I think if you want to go in that direction, you need to go broad first so that you don't miss anything. And then maybe if it's appropriate for you to narrow things down. So we have a question about what shear rate did we use in the cell culture media experiments? Are media non-Newtonian?
So with the cell culture media, I had to use exceptionally high shear rates in order to generate enough signal on our chips, since they're low viscosity fluids. So I believe I ran them at 20,000 reciprocal seconds. That's the maximum on our BE05 chip line. At the time, that was the most sensitive to low viscosity fluid chips we had on our Initium unit, which is our automated system. And generally speaking, based on what's inside cell culture media, I would assume that they are Newtonian under the broadest shear rate range that we can test. However, that's just for the DMIM and the F12 and the FBS. There may be some media that have some large length scale nutrients of some sort that may induce shear thinning. They may have large scale particles that could also cause these fluids to shear thin, but the media that I used for these experiments were Newtonian.
Okay, and while we wait for any additional questions, did you have any additional advice for people new to rheology? Since, when you came here, you were new.
Yeah.
Did you have any lessons to share?
You're new to rheology, I would say don't be afraid to get your feet wet, and then also be mindful that the instrument will give you a number regardless of whether the data is good quality or not. And that's for any instrument. That's rotational instruments, that's our instruments. Even if no matter what, you're going to get a value, but is it the right value? I would try and get a confidence and understanding on what does good data look like and what does poor data quality look like and what are data artifacts. That's something that I didn't really understand. Previously, my only experience with rheology was hydrogels on a parallel plate rheometer in graduate school, and yeah, I could get a number no matter what I did, and I didn't really understand why. And so that would be my tip, is to just be mindful of your data and try and figure out if you're experiencing data artifacts or if this is real data.
Yeah, just to add a couple more points to that. That is one reason why we always emphasize that viscosity is a calculated property. So I don't know what types of instrumentation everyone is using, whether some are using ours or some are using rotational instruments. Certain software will flag you and give you a warning if they think there's something wrong, but that's not always the case. So as Zach said, you do want to get familiar with going beyond just looking at the table or the plot that the software gives you. And for example, go in and look at the transient curves and try to understand the features there and the timing you need to get to a steady state velocity profile in the particular tool that you're using. So that's a good comment that Zach brought up. You want to don't maintain a superficial understanding, go in and start understanding what the calculation involves, and then look at all the supporting information that you can from the software rather than just the final bit of data. So I think we didn't get any additional questions there. So I think we'll end. So thanks everyone for joining. As always, if you signed up, you'll get within, I would say less than a week, you'll get an email giving you a link to the presentation, and then also the recording. And also you probably have a contact information. So if you have questions that you didn't think of during the actual webinar, feel free to contact someone in our office with any questions that come up for you, and we'll get back to you. So thanks again for joining us today.
Thank you.